Hi, everyone. Today we'll be presenting our hydrology site presentation. We are JTV Squared, a water consulting firm. Here are the contributions of the members for this report. So this project is a proposed site plan for the new stormwater management system for a new multifamily residential development in Atlanta, Georgia. This project is a proposed design of the infrastructure that is needed to properly manage the rain runoff as well as other sources that is specified in the Georgia Article 10 Post-Development Stormwater Management as well as Georgia Stormwater Management Manual. The existing site is a green field bordered by roads on its periphery and presents a variety of existing site conditions. The topography of the site features relatively flat terrain with some elevation differences. The site has no vegetation other than grasses and sporadic shrubbery. Utilities such as water supply, sewer systems, and electrical infrastructure are accessible from the adjacent roads, simplifying connections for construction. Overall, the existing site conditions provide a promising foundation for the development of the site. The greenfield site, approximately spanning 11.25 acres, exhibits diverse and dynamic characteristics that contribute to its overall suitability for this design. Here is the drawing of the existing site. Proposed site description. New proposed site will now include a new multifamily residential complex that consists of a parking lot, 3 courtyards, and a 2-story apartment building that's around 132,000 square feet. For the stormwater management, the site will comprise of concrete pipes with either 12 or 18-inch pipes. The proposed site is primarily covered by concrete and asphalt, and the apartment complex roofing. High runoff coefficients mainly ranging from 0.6 to 0.9, and 23 proposed 4 points. Here is the drawing of the complex on the existing site. And I will pass it over to Bree.
Hi, I'm Brianna, and I'll be discussing the Georgia Stormwater Management Manual design criteria and the design standards in which we are limited to are the following, which is the hydraulic gradient should be kept within limits to ensure that the velocity remains below 15 feet per second. The minimum desirable physical slope should be 0.5% for the slope that will produce a velocity of 2.5 feet per second when the storm sewer is flowing full, whichever is greater. The storm drain system should be designed with increasing flow velocities along their length, and the upper reaches should feature gentle slopes compared to the lower reaches. And a minimum time of concentration is 5 minutes with maximum sheet flow length of 50 and or 100 feet, depending on site conditions, in which we utilized 100 feet. The design methodology used was pipe design. We used the rational method. Time of concentration utilized the tier 55 method using the largest time of concentration value. The runoff coefficients were determined from the Georgia Stormwater Management Manual Volume 2, and the precipitation values were obtained from SSA and the IDF curve from the NOAA Atlas 14. The figure below shows the site to be developed in which these subbasins were delineated based on nearby inlets, and the following figure is a close-up view of the basins and inlets as well. The watershed table listed provides an accurate description of each of these subbasins, as well as the area determined on the CAD drawing. The runoff coefficients and time of concentrations are products of the storm and sewer analysis, and now I'll be passing this over to Jordan.
All right, so here is a list of all of the inlets we have within the site. And the types of inlets. We use the F.DBI type A on SAG, and on this chart is also the elevations and the offsets. So on the next slide is the outfalls located on the proposed development. So we have 3 outfalls, 2 on the right, on the west side, or the east side, and one on the west. And here are the elevations for all 3 of those as well. Here's a chart of all the pipes we have, with the inlets and outlets connected to them, as well with the inlet elevations and outlet elevations as well. Here are the characteristics of the pipes, along with the slopes and the shapes. They're circular, and then we used 12 inches and 18 inches diameter for those pipes, as well as concrete. And here are the analyses that we did. So we did a 1 year, 2 year, 5 year, 10 year, 25 year, 50 year, and 100 year. And as you can see within all these, the velocities are below the 15 feet per second maximum, and they all have relatively low peak flows. And here are the scale profile plots for all of the piping systems we have within the proposed site. As you can see, most of the slopes are lower at the top and get steeper as you get closer to the outfalls. And for the detention basin design, we use the SCS method. And within the SCS method, we needed the curve numbers. So here are the curve numbers we have for those sites. So for pre-development, we have a curve number of 48. Post-development, we use a weighted curve number of 68, as 40% of it was impervious, and the rest of the 60% was the existing 48 curve number. And here are the hydrographs calculated with that SCS method. We have a 1 year, 2 year, 5 year, 10 year, 25 year, 50 and 100 year as well. And for the 100-year calculation or hydrograph, we use that to calculate the detention basin volume. We got roughly 89,000 cubic feet. I will pass it off to Brandon now.
For the stormwater BMP or best management practice, we decided to use a dry detention basin. A dry detention basin is a type of stormwater BMP that captures stormwater runoff temporarily to reduce downstream flooding and remove pollutants. Some of the key features of our dry detention basin are the embankment, which impounds water to reduce downstream flooding, the sediment forebay, which slows incoming stormwater runoff and allows sediment to settle, and the outlet control structure, which contains a low and high orifice that allows water to bypass the basin and prevent the embankment from overtopping. Some key advantages to dry detention basins as a best management practice are moderate removal of urban pollutants, high community acceptance, and useful for water quality treatment and flood control. Some disadvantages are that detention basins can be problematic for low relief terrain, and there's potential for thermal impacts such as downstream warming. Some maintenance requirements for dry detention basins are the removal of debris from inlet and outlet structures, the maintenance of side slopes and outlet control structures, the removal of invasive vegetation, and the monitoring of sediment accumulation and removal periodically. This results in a pollutant removal of 60% of total suspended solids, 50% of removal of metals, including lead, zinc, and cadmium. Now, for the design criteria, we decided to design for water quality volume, which is the stormwater runoff storage volume required to capture suspended sediment before it is transported to receiving waters. We calculated this using the water quality formula provided in the Georgia Stormwater Management Manual that determined that there should be a minimum water depth of 1.2 inches. We also calculated the runoff reduction volume, which also was provided by the Georgia Stormwater Management Manual on how to calculate, and we determined that to be 16,738 cubic feet. Now I'll pass it on to Tori.
Continuing for design criteria for our channel protection, we used our weighted post-development curve number 68 for initial obstruction, including surface storage, interception, evaporation, and infiltration. Number we found would be 0.941. The potential maximum runoff at 1 year at 24 hours was found to be 3.36, found from NOAA Atlas 14. Time of concentration calculated in SSA was 0.802 hours. The unit peak discharge was found to be 350 CSM, and the flow post-development volume of runoff was found to be 1.114 cubic feet per hour, giving us a channel protection value of 0.66 acres per foot, or 28,783 cubic feet. So, and the type of basin was to be determined to be a dry basin. And this is an image showing of what that would be after the 1 or 24 hours. This is the basin drawing in CAD from a bird's eye perspective. Using the trapezoidal prism volume, we found the best size of our prism or basin to be 145 feet in length, 95 feet for long base, 65 feet for short base, and 8 feet deep. We rounded the volume around to 92,800 cubic feet to take into account the rounded edges of the basin. Here is a drawing of the pipe layouts. The pipes from the outfalls to the basement are 32 feet in diameter. And this is the OCS location on the south middle of the basin. And here is another image of what it would look like in real life. And I'm passing it over back to Brianna.
So the outlet control structure was designed with a length and width of 4 feet and a total depth of 9 feet, which kind of encompasses the entire depth of the basin with an additional 1 foot of freeboard as well. We have in the upper left quadrant design of the head wall or discharge conduit in which our stormwater will exit through of an estimated 18-inch pipe. 1.25 inch, 3.5 inch, and 4-inch orifices were used for this project, as well as a 3.72 foot weir length that was determined and displayed in the bottom right figure. And the bottom left figure displays the section view of the entire OCS, which contains an orifice, inlet pipe, weir, riser, manhole, and the discharge conduit. This next slide is just a sample calculation that was used for this project. So this was designing for the first year. So what we calculated was 2 orifices were needed with a diameter of 1.25 inches. These are our hydrographs for storms leaving the outlet structure. So again, we have the 1 year, 2 year, 5 year, 10 year, 25 year, 50 year, and 100 year runoff with pre-peak and post-peak values displayed in the bottom right quadrant as well. The storage curve data for basin stages is also listed. We have the depths from 0 to 8 feet, and then the areas and volumes were calculated and determined on SSA as well. The summary table for peak flow rates and for all mandated design storm events are listed below. In the left table, we have the storm events, sizes of the orifice and weirs, the numbers required, and the crest elevations as well that was determined on SSA. And in the right table, we have storm events, pre-development peaks, post-development peaks, and then post-development peaks, including that storage as well. And at this time, we would like to